Hi, mechanical engineers. Welcome to Royal Mechanical. In this live streaming, I am going to design a drill jig step by step using Catia V5. The problem what we are trying to solve here is we have a raw material which is a rectangular plate, and we need to drill a simple hole within this rectangular plate. That is a problem statement what I have today, which we will try to solve by the end of this live streaming session. Before I get started, let me introduce you to Royal Mechanical. Royal Mechanical, we have a vision to provide free job-oriented certification courses for mechanical engineers. Basically, our objective is to enable mechanical engineers to start their careers and also excel in their career. Now, coming back to the hole, there are no products without a hole. You can look at any of the products, okay, you can find a hole within that product. For example, okay, let us take an example of an aircraft or an airplane. You can find umpteen number of holes within an aircraft. Basically, these holes are used to fasten. For example, if you look at the skin of an aircraft, you can find rivets where the skin is fastened or riveted to the structure, body or the fuselage. So now these rivets, you need holes. Similarly, okay, if you look at a car or any vehicle for that matter, you can also find holes within them. You can look at robots, you can find holes in them. And these holes are generally used for assembling the parts together, so that all these parts put together will make a system, and then it will make a product so that it can function properly. So now, going back to our problem statement of the rectangular plate, and then this rectangular plate, okay, to just to make the problem very specific, let us think, okay, we have a rectangular plate of length 100 mm, width 50 mm, and thickness 10 mm. We need to drill a hole in this rectangular plate of dia 10 at a distance of 25 mm from the edges, what you are seeing on the screen. So how are we going to drill this hole is the first question. And how are we going to drill this hole? Okay, if we have hundreds of such plates, why we need to think about hundreds of such plates? Let us take an example of a car. For example, if you have to make a car in a mass production environment, if there is a company, okay, which is going to manufacture cars, they are going to manufacture thousands of cars in a day. So if you have to make holes in any one single component of a car, so you have to make thousands of such parts, and then okay, you'll have to make holes in each and every part, and that's the design requirement. So how are we going to do it? Do you have any idea? The other thing is, each and every hole which we make within that component should be accurate and precise. Accurate in terms of the dimensions. For example, look in the rectangular plate, what we have, if we tell the diameter of the hole should be 10 mm, and then it should be positioned at a distance of 25 mm from the edges. So then it has to be accurate, and then it has to be precise in the sense, okay, when I'm making hundreds of such parts, the variation should not be too much. It has to be quite precise as per the design requirement. So to start with, we have this raw material, which is a rectangular plate, and then this will be the finished product. Let us look at, okay, how we can do it, okay, in a kind of environment, okay, maybe probably, okay, when you did your engineering within your simple mechanical workshop, what you had in your engineering college. So you will take the raw material, and then you will use a scriber and then a tri-square, and then you are going to mark 25 mm from one of the edges, and then you will scribe a line, and then this is what you get. You will get a vertical scribed line at the distance of 25 mm from one of the edges. Similarly, okay, you are going to repeat the process with reference to the other edge, where you are going to mark 25 mm, and then you are going to scribe another line at a distance of 25 mm from the other edge, and you will get two lines, okay, which are intersecting. So you have an horizontal line at a distance of 25 mm from one of the edges, and you have a vertical line which is at a 25 mm from the other edge. So once you identify this intersection point, this is where we need to drill the hole. To drill the hole, we will have to make a center mark, okay, using a center punch. And then this is what we end up with. So we have a rectangular plate with the mark, center mark, okay, which we'll be using for drilling. And then we are going to take this raw material and then hold this raw material in a machine vise. This machine vise is present in the drilling machine. And then I'm sure all of you are aware of how a hole is made. Basically, a hole is made on a drilling machine using a drilling bit. And then to be very specific, these machines are called radial drilling machines, which are present in industries. And then there is a machine vise, okay, which is present on this radial drilling machine. You are going to hold this raw material or the workpiece in the machine vise, and then you are going to drill the hole. Once you drill the hole, okay, you'll have to take the rectangular plate out of the machine vise. So you have the end product, the rectangular plate with a simple hole. What you observe, this is a very tedious process. We need to mark, then we need to scribe, then we need to punch, and then we need to hold it in the vise, then we'll have to drill, and then we'll have to take it out of the vise. So a very tedious process. Because of this tedious process, what happens is, this is going to be of a very low productivity activity, especially in a mass production environment. If I ask a technician to drill a hole in this fashion, he is going to take a lot of time. When he is taking a lot of time, means, okay, he'll be able to produce very less parts in a work day. For example, okay, if he's going to start working in the morning and by evening, okay, he's going to make very less number of parts. And because it's a tedious, boring activity, it becomes low productive. And then the marking, the scribing, the punching, and the drilling, for all these things, the skill of the operator comes into picture. So this will be dependent. What will be dependent? The accuracy and the precision of the end product will be dependent on the skill of the technician. So it will be skill dependent. And when the technician is making hundreds of such parts, there could be a possibility of some amount of human error, which will creep in while either marking or punching or scribing or drilling. So there will be no repeatability in the parts. For example, we need to ensure that the position of the hole is at a distance of 25 mm from the edges of the component. The operator might drill at some variation. For example, 25, some components might come 25 plus 1 mm, some components might come 25 minus 1 mm. Sometimes it could be more. So what is going to happen is, okay, basically there is no repeatability in the components. What is going to happen when there is no repeatability? When there is no repeatability, okay, when we have to take this part, okay, into an end product. Like for example, okay, if we have to make a hole in one of the part, okay, which goes into a car, and then these parts are coming in variety of dimensions. Some of the parts might not fit into the car. Even if they fit, okay, they might not function properly in the car. So these are some of the disadvantages of creating a hole within a manual environment, where the technician is using his skill to create the hole. So now, what's the solution for this? How is the industry addressing this problem? Are they taking all these components, marking, scribing, holding it in the vise, drilling, and then ending up with some non-accurate parts? What are they doing with this? Are they throwing away these parts? If they are going to throw away these parts, okay, what is going to happen? It's waste of time, material, money, everything. But an industry can't afford to make these type of errors. So they need to figure out some solution to make accurate and precise holes. What is that solution is? That is drill jig. This is how engineers solve the problem of inaccurate and reduce the wastage whenever they are making parts for an aircraft or for a car or for a robot or for that matter, okay, any such products. A drill jig is used to drill accurate and precise holes in any component. Before we get into understanding what exactly is a drill jig, let us understand the parts of the drill jig. The parts of the drill jig consists of the top plate, what you are seeing here. On the left side, okay, what you are seeing is the drill jig, and on the right side, what you are seeing is a cross-section view of the drill jig. The top plate, which houses a drill bush. You are seeing the drill bush. The drill bush is housed in the top plate. Then we have the locators. Right now, okay, just understand what are the parts of the drill jig. Later, okay, you will get a better clarity of all these parts. And once I start designing, okay, you will have a clear understanding of each and every part, the functionality of the part, and how it is designed using Catia V5. So these are the locators. And then we have the workpiece. The workpiece is the one on which we are going to drill the hole. We have a clamp to hold the workpiece in the position. And then we have support pins, the support pins on which the workpiece is sitting. And then we have the bottom plate. This bottom plate, okay, on which the entire components of the drill jig are mounted. And this bottom plate is also used to mount on the drilling machine. Here we have a better view. What I have done here is I have hidden the top plate and the clamp so that you can have a better clarity. We can see the 3 support pins on which the rectangular plate or the workpiece will sit. And then we have the front locator, 1 front locator and 2 side locators. Now you can see very clearly, you can see the workpiece sitting on the rest pins and in between the locators. You can see the workpiece sitting on the 3 support pins in between the locators, the front locator and 2 side locators. Now the operator can push the raw material against the front locator. He can push it using his hand so that the workpiece will butt against the front locator. Then we have this clamp which will hold the workpiece in position. In this case, I have not shown the top plate for better clarity. Now you can see the entire drill jig. You can see the workpiece and then the drill jig and then the drill which is going through the drill bush and then drilling the workpiece. I'm sure, okay, you can imagine the drilling process. So this is how the raw material, which is a rectangular plate, will go through the drill jig, and then we will have the finished product where the hole is drilled in the rectangular plate. And when we are using the drill jig, okay, we are going to get accuracy and also precision. Each and every part are going to be similar, and then the hole drilled will be accurate. How it will be accurate? Because we are going to position it in between the locators and then clamp it in position every time. So every part will get into the same position, get clamped in the same position, and then the drilling will happen through the drill bush. So we will get accurate and precise components. This is how accuracy and precision is ensured in a mass production environment. So to define what is a drill jig is a tool used to locate and hold the workpiece and then guide the drill to create accurate and precise holes in the workpiece. So this is the definition of a drill jig. So that was some things on the concept of why a drill jig is essential. So now this video which I am making, I'm not going to touch upon a lot of theory. This is going to be mostly a practical session where we will be designing, or I will be demonstrating how to design this drill jig using Catia V5. We are going to do this. But theory is also very essential for anybody to understand what a drill jig is. But I am not going to cover any of the theory. So what I would recommend you people is go to YouTube. There is a lot of material within YouTube or Google where you can get to know a lot of theory about drill jigs. One of such material which I would recommend is the NPTEL video on jigs and fixture design. Jigs and fixture design. NPTEL jigs and fixtures. Here you can see there is one video, lecture 33, jigs and fixtures for machine shops. A very nice video which you can go through for the theory. So here the problem statement what I am trying to address is covered in this lecture. Please go through this for all theory. Understand the theory if you are more theory oriented, but if you want to understand actual design, so we can get started with the design. The first step is to design the workpiece itself. So this is the workpiece what we have. So let us get started with Catia v5. Let's create a new part file. So we are going to enter the part name as workpiece, or we can also put it as a rectangular plate. Leave all other actions as is. So now we have a new document or the part file with the name rectangular plate, and then we have 3 default datum planes. So I would use the position sketch command to create the initial sketch. So I'm going to make a sketch on the XY plane. I would always prefer to swap the horizontal and vertical axis and then reverse V. So what happens is when we are going to bring the orientation of H towards X axis and V towards Y axis, so this will give the perfect top view. So this is what I would do. And let us sketch a rectangle using the rectangle command. Let us create the dimensions by adding 1 dimension to length and 1 dimension to width. So what you need to do is, okay, you need to double click the constraint command. So this is a dimension command known as constraint. So if you double click, the command would repeat. Let me demonstrate it once again. Let me delete these 2 dimensions. So if I'm going to click it once, I can create only 1 dimension. I can't create the second dimension. So if I'm going to double click, I can create as many dimensions as I want. So I have dimensions, but the sketch is not fully constrained. You can see we have 2 white lines. It is very essential when we are working on Catia or any other CAD software that the sketch should be fully constrained. But we have given both the dimensions, the length and the width, but still the sketch is not constrained because the positioning of the rectangle is not defined. So what I would do is I would add a symmetry constraint to the top line, the bottom line with reference to the horizontal axis. Select the constraints and then apply a symmetry constraint. So now the sketch is fully constrained. I'm going to change the length to 100 mm and width to 50 mm. Exit the sketcher workbench. So now I have the sketch. So using this sketch, I can create a plate using the pad command. I'm going to select the pad command and then select the sketch. The thickness of the plate can be 10 mm. Click on preview. Make sure that the plate is created and then OK. So now we have the rectangular plate. So before proceeding, let me save this file on my local hard drive. It is always better to frequently save so that we don't have any data loss. Next, we'll create a hole using the hole command. Pick the hole command, select on the surface where you want to create the hole. I want a diameter 10 hole and I want a through hole. So if I want a through hole, I'm going to pick up to last. And then I need to define the position of this hole, that is 25 mm from both the edges. So I'm going to select the positioning sketch. So what I need to do is I need to make the dimensions. So now this is the center of the hole. I can drag it wherever I want to. So I need to create the dimension 25 mm between one edge and the position of the hole. So this will be 25 mm. As the width of the plate is 50 mm, I would constrain it to the one of the planes, that is the center of the plate. Take the constraint and then put a coincide. So now you can observe that earlier, okay, the center of the hole was white in color. Now it has turned into green. That indicates that the sketch is fully constrained. Now I'm going to exit the sketch. You can see the hole is getting created. Let me click preview. Okay, I have the hole. I can tell okay. So put the orientation into isometric view and then zoom all, that is fit all in. And then let me save the file once again. So now I have the workpiece ready. I have the rectangular plate with a simple hole. So now what should we do to design a drill jig? So there should be some process, right? So now we have the workpiece ready. That is, we understand what is the raw material and then we understand what is the end result or the final product. How are we going to design this? What are the steps we are going to take? Let me just show you what could be the steps. So now, as you understand, the first step is to have the component drawing or understand what is the end requirement. Or we could also call this as the final component drawing. So in our case, the final component drawing is a rectangular plate of length 100 mm, width 50 mm and thickness 10 mm. And then we need to make a hole at 25 mm from two edges. So that is the final component drawing. And eventually what we want to do, what is the end result, okay, we want to achieve? The end result, what we want to achieve is, okay, we need to have a jig design or drill jig design. This is the end result what we want to achieve. So when I tell drill jig design, okay, what specifically it consists of? So basically it consists of the 3D design, that is a 3D model, and the 2D manufacturing drawings. This is what has to be achieved. The 2D manufacturing drawings are the ones which we are going to give it to the tool room or the machine shop, and basis these 2D manufacturing drawings, okay, they are going to manufacture the drill jig. That's why the manufacturing drawings are very, very important. And to create the manufacturing drawings, okay, we need the 3D data. Why we have to do 3D design? We have to do 3D design because first thing is, for a designer, it is always very easy in the sense, okay, he can visualize the design with a lot of clarity. That is point number one. Point number two is he can make changes, okay, within the design very quickly. For example, tomorrow, okay, we have one another plate of size probably like 150 mm length, and then we need to make a hole of size 15 mm within that plate. So then what we can do is, okay, we can pick this design data, the 3D data, and then quickly make the changes, and then we will have the new design ready for the new requirements. That's the advantage of the CAD program. So 3D, which will enable a designer to visualize and then make any modifications in a quick manner, and manufacturing drawings so that it could be manufactured. Any design has to be manufactured. Design can't just stay on CAD systems. This is something which every mechanical engineer should understand. Designs should not lie just in CAD. Okay, they should be manufactured, and then once they are manufactured, they have to function the requirement which they have to perform. So now, what we have is the final component drawing. And what we need to give is the drill jig design, 3D and 2D manufacturing drawings. In between, what we are going to do? In between, what we need to do is the first step, once we receive the final component drawing, is to study this component drawing and then understand the requirements clearly. Why study the component drawings? Simply because the current problem statement, what we have is a very simple problem statement where we have just a rectangular plate and only one hole to be drilled. But when it comes to an actual industrial requirement, that need not be the case. It could be slightly complicated. You might have to drill many number of holes of many diameter. The plate not be a simple plate. The shape of the plate could be quite intricate. So it will be very essential for you to study the component drawings and then understand the requirement. What type of holes, where it has to be drilled, what is the location, what is the size, all these things. Once you study the component drawings and understand the requirements, the immediate thing that has to be done is create a concept. What is a concept? Concept or concept design. Concept or concept design is the idea basically. What is the idea which you are going to use to solve the problem? How are we going to make the concept design? I generally recommend that concept designs be created using sketches. So for the current problem, what I have, let me show you. If I have a picture, let me just check if I have it. So what you are seeing is the sketch, what I have done as a concept drawing. Let me just grab a snapshot of this. So this is a concept what I have created. So I have made a sketch. I have made the sketch of the workpiece and then the hole, and then I'm showing, or I'm deciding, okay, where I'm going to put the locators, where I'm going to put the clamp, and then how I'm going to guide the drill so that I'll get an accurate hole on the workpiece. So the locators are going to ensure the accuracy and precision on the component side. And then the drill bush is going to ensure that I'm going to drill, or the technician is going to drill the hole precisely, accurately and precisely at the location as per the requirement. So this is the concept sketch what I've done. Once the concept sketch is done, okay, then this could be discussed with any senior designer or a supervisor, and then finalized. Okay, how many locators are we going to use? What kind of clamp are we going to use? Is this design feasible? Would it be better to spend more time and then develop this concept design? The senior designers or the supervisors, okay, will have more experience. They will guide younger engineers to improve upon the design. So once this concept design is done, this discussion with the supervisor or senior designers, I would like to call that as a concept design review. So basically, okay, we are getting the concept reviewed by the supervisor or a senior designer. So for the review, what are we going to present? We are going to present the sketch what we have made. This sketch what we have made, okay, we can present it, explain it to them the way I am doing it to the supervisor, and then get any feedback from their experience and as per the requirement. So once the concept design review is completed, so what we need to do is, okay, we will have to do something called detailed design. Detailed design or detailed design, both are the same. So what is detailed design? So now we are going to go to any CAD program which is prescribed in the company. So right now I'm going to use Catia V5 CAD program for doing the detailed design. So in detailed design, we are going to develop the concept into a detailed parts, assemblies, everything. We are going to decide upon what should be the size of the base plate, what should be the size of the locator, what is the size and shape of the clamp, all these things. So basically, we are going to use a CAD program during detailed design. It doesn't mean that during concept design, we should not use a CAD program, only sketch is done. Sometimes it is always better to make the concept also in a CAD program for better visualization for the design engineer, as well as I told you earlier, this problem statement is a very simple statement where we can make sketches in an easy manner. Whereas when the problem statement becomes complicated, it might be really difficult for us to make a sketch and explain to the other person. But I always recommend to make a sketch because that clears a lot of doubts, whatever we have. If you get into the CAD program, a lot of time could be wasted in developing ideas. So sketches, okay, we can quickly make some sketches, understand what we need to do or how we need to proceed on the design. So once the detailed design is done, that is okay, we have the 3D design. Basically, detailed design generally can be 3D. And then we can have again a detailed design review. Again, we can take this 3D model either in the form of CAD program itself, or sometimes, okay, we can make presentations and then present this to the supervisors or our seniors, or sometimes to customer as well, and then take the feedback and then make any changes. If at all, if okay, we get some design improvement ideas, or sometimes there could be some errors in the design, which the supervisors and senior designers could point out. So we can make the changes. And then once the review and corrections are done, we can go ahead and create the 2D manufacturing drawings. So once the 2D manufacturing drawings are created, again in Catia V5, we need to get approval. For. So now we have approval for manufacturing. Manufacturing of what? Manufacturing of the drill jig itself. So now this last step what we had put is not relevant right now. So these are the steps which are used for designing a drill jig, or for that matter, okay, any mechanical component. So let's have a closer look. we have the final component drawing. Basically, okay, the final component drawing is nothing but the requirements. So we are going to study the component drawings and then make the concept design. So we will have the concept design review. If at all, if any mistakes are identified in the concept design review, we'll have to correct it. So let me just ungroup this. So if there are any mistakes or any improvement areas, so we'll have to redo the concept design. Similarly, if we have any improvement areas identified during the detailed design review, we can do the same. The same thing happens when we are doing the 2D manufacturing. When we are going for approval, again, the drawings will be checked and then we will have to redo it. This has to come to the detailed 3D design. So to summarize, we are going to study the component drawing, make the concept design. After making the concept design, there will be a concept design review. Any corrections, updates, will go back again, we'll have to redo it. And then we'll perform the detailed design. That is, we'll complete the 3D. After the 3D detailed design, we will undergo the design review. Any updates, corrections will be again brought back to the detailed design stage. Once it clears, okay, we'll create the 2D manufacturing drawings. Once the 2D manufacturing drawings are completed, we are going to release these 2D manufacturing drawings for manufacturing. Prior to manufacturing, we need to get the approval for manufacturing from the head of the department. And then if the head of the department is making any suggestions, we'll have to incorporate them. And then this is the procedure. So this is the procedure, okay, which we'll have to do. So now, as I told earlier, I made the concept design. I made a sketch of the concept design. So pretty much the concept looks good. Let us get started with the detailed design. So now, before we get into the detailed design, we need to create, let us create a product. Product is the assembly file in Catia v5. I'm going to create a product. Let me save this product as jig for rectangular plate. And then let me assemble the workpiece. So to assemble the workpiece, I'm going to use existing component with positioning command. Click this and then click the product. And then let us go to our hard drive, wherever we have saved the rectangular plate. So I'm going to select the rectangular plate. You can see the rectangular plate comes into the assembly, and I'm going to constrain it using fixed component. So it is good that, okay, the first component will be always fixed. It is a common practice that we change the color of the rectangular plate to either yellow or red. So right click on the rectangular plate, click on properties, come to graphics, and then change the color to yellow. It's a common practice that the workpiece will be generally either in a yellow color or red color. I generally prefer to go with the yellow color. So now we have the drill jig assembly file ready, and then we have the workpiece ready. So now the first thing what we would do is at a technical level. At a technical level, we already have an understanding, okay, how the workpiece is loaded onto the drill jig. So we are going to position the workpiece. Let me go back to my presentation. So what we are doing here is we are going to position the workpiece on the support pins in between the locators. So this is the first thing what we'll have to do. We will have to design the locators and the support pins. And then the second step would be to clamp the workpiece. Once we have positioned the workpiece, we will have to clamp the workpiece. So the second step would be to clamp it. So we'll have to design the clamp. So coming back to my explanation presentation. So the three major steps, the technical steps is the first step is design locators, design clamp, and then other things like drill bush, the drill plate, base plate, everything. So let us put it as the jig plate and base plate. So what we have is the first step would be to design the locators. The second step would be to design the clamp, and then all other components like the jig plate and the base plate, okay, which are very critical components. So let us get back to the Catia session. So first thing is to design the support pins. The support pins, I generally prefer to design the support pins in a circular pattern, that is a cylindrical support pins. So let me just go create a new part file. I'm going to enter the part name as support pin. And then I'm going to make a sketch on the YZ plane. So to create a support pin, I will be using the revolve command. So let me create the shape first. So I will have the head of the pin, and then the shank, okay, which will get inserted into the base plate. Let me create the axis from here, that is the top point, to the bottom point. Now we need to create the dimensions. I'm going to select the axis and then the outer dia. Right click here and then swap radius to diameter. So I need the diameter dimension. Similarly, I'm going to select the axis, the outer dia, right click, radius diameter, I'll get the diameter dimension. Now the height of the head and then the height of the shank. The sketch is totally constrained. So here what I will do is maybe I will choose some 8 mm as the shank dia, probably 12 mm as the support pin dia. Let me take this as another 10 mm. Maybe this as 10 mm. I think looks good. So I have the sketch ready. So now I can use the shaft command, and then I'm going to revolve it for 360 degrees. So now I have the support pin. So what we need to do is, let me first save the support pin. As you have seen in the presentation, you can see that the support pin is housed in the base plate. So we will have to drive the support pin into the base plate. So if I have a sharp edge, so it will be very difficult for me to drive the support pin inside the base plate. So we'll have to make a chamfer. Let me make a chamfer at this edge. So generally, okay, this is called an entry chamfer. So generally entry chamfers are of 15 degree. Probably I'm going to make this 3 mm. How do you decide it as 3 mm? Okay, this all comes with experience. So you'll have to do many projects. Let me preview and then tell okay. Yeah, now this looks good. it will be better to add a small radius here of maybe 0.5. Let me see how it comes. Not bad. Now we have a small radius. So now it will be easy for us to drive the support pin into the base plate. The sharp edges is not advised here. So I'm going to put a chamfer here to the sharp edge. 0.5. And this chamfer is to just avoid the sharp edge. So let me put 45 degree. So now here, this portion is again sharp. Let us put a fillet in this portion. 0.5 mm. Okay, looks good. So now the support pins. I've saved it. It's always advised that we put the view into isometric and then fit all in before we save. So now let me come back to my drill jig product. So now we need to position the support pins. So what we would do is to position the support pins. Okay, let us just make a base plate, a tentative base plate. So let us create a new part file, base plate. I'm going to create a position sketch on the XY plane. I'm going to swap the horizontal and vertical axis, reverse the vertical axis. So now what I'm going to do is I'm going to make a rectangle here. Observe, okay, what I'm doing is I'm going to create the rectangle from the origin, all around the origin. I'm going to create dimension, 4 dimensions. I'm not going to create dimensions for the length and width to start with, because I don't know, okay, what is going to be the length and width at this point in time, because the design has to get frozen. So I'm going to create provision so that I could alter the length and width easily. So what I would do is I would make this tentatively 50, maybe 60. These are just tentative dimensions. So now I'm going to create the plate using the pad command. I'm going to use a 20 mm thick plate, preview. Okay, it is coming out good. Let me save the base plate onto my hard disk. Now what I'm going to do is I'm going to come back to the drill jig product. Now what I need to do is I need to assemble the base plate. I'm going to use existing component with positioning, select the product, and then I'm going to use the base plate. Now you can see the base plate has come into the assembly file. It is sitting on the workpiece. So I'm going to hold it and drag it below. Okay. Maybe it didn't come properly. I don't know. Okay, it got tilted. So I'm going to delete it and then bring it again. In the sense, I'm going to assemble it again. Bring the base plate. I'm going to leave it as is. This time I'm not going to fix, use the constraint fix component, because I need to use a different set of constraints. I'm going to use the manipulation command and then select Z direction, hold the base plate and then move it in the Z direction. I'm going to click OK. Now this looks positioned properly but not accurately. So what I would do is I need to define the constraints. First, I will give an offset constraint between the top face of the base plate to bottom face of the workpiece. I'm going to put that as 10 mm. If you remember, 10 mm is the size of the head or the height of the head of the support pin. So it is going to sit at 10 mm. Now the other thing what I intend to do is I need to align this plane and this plane. Similarly, let me align the other set of planes, this and this. So now you can see the constraints are created, the offset constraint and two coincident constraints. Now you can see how it is. You can see the offset 10 mm and these planes are coincident or in alignment. So I will leave it as is. So now I need more length in this direction. I need more length in this direction. I'm going to go to the base plate, double click the base plate, and I'm going to change this 60 to 120. Come back to the assembly file. Now you can see. So now you understood why I created a different dimension scheme for the base plate. We can edit this sketch and then probably add overall dimensions. You can see the overall dimension is not coming because this is telling, okay, it's a redundant dimension. So let us create that as a reference dimension. 180 mm length and 100 mm width. Let it be like that time being. Now what I need to do is, okay, I need to make holes for housing the support pins. So generally, okay, I recommend that we create points for positioning the holes. So what I would do is I'm going to create a position sketch on top of the base plate. I'm going to swap the horizontal and vertical axis and then reverse the vertical axis. Okay. Let me create a point using the point command. Double clicking, I can create multiple points. I'm going to have one point at the center and then 2 points like this. Let me dimension the points. Like this. And then I can put a symmetry constraint between these 2 points with reference to the horizontal axis. Select the point 1, then point 2, and then select the horizontal axis. Then the constraints will get highlighted and then I can put a symmetry constraint. Now you can see everything is green in color. I want to put this at some 20. This at some 25 mm. Tentatively, I need to finalize it later. Tentatively, I'm going to position at these positions. And then we need to create a hole for inserting the support pins. So I'm going to select the top surface of the base plate and then this point, and then pick the hole command. The shank dia was 8 mm dia. So I'm going to select it as 8 mm. Depth, I want it up to last, that is a through hole. Click OK. So I have one hole. So now I need to repeat the same hole in the other 2 positions. So what I'm going to do is I'm going to use a user pattern command. So user pattern command and then positions. Positions are nothing but the points what I have created. And then the object is the hole. So now you can see the same hole gets repeated on all the points. So now we have the 3 holes. I'm going to save the base plate, come back to my Jig Assembly file. Time being, what I would do is I would hide the workpiece so that it will be easy for me to work. I'm going to select the same existing component with positioning, select the product, and then the support pin. Now you can see the support pin has come into the assembly. Now I am going to align the center of the hole with the center of the pin. And then I'm going to put a contact constraint between the top plate and then here the bottom of the head. Now you can see the pin is sitting perfectly inside the hole. To check, we have this sectioning tool. Click on the sectioning tool and then you can see a plane comes. What you can do is go to result and then pick on volume cut. So if you see the volume cut, you can see that it is nicely sitting. The pin is nicely sitting inside the base plate. Let me cancel this. So now what we can do is we can assemble the remaining 2 pins. I would redo existing with the positioning. Select the support pin. Again, I will do once again. Okay. Use the manipulation command and then move the pins so that it will be easy for me to assemble. I'm going to put a coincide constraint, not with the plane. Put a coincide constraint with the axis of the pin to the axis of the hole, and then put a contact constraint between the top surface of the plate to the bottom of the head. And then you can update. The pin comes to position. Let me do the same thing with the other pin. Axis of the pin to the axis of the hole, coincident constraint, and then contact constraint between the bottom and the top. So now I have the pin. What I will do is I will unhide or show the workpiece. Now you can see that where is the pin sitting? The pin is exactly sitting below the hole. This is not correct. If it is sitting exactly below the hole, how am I going to drill? It is not possible to drill, right? For me to drill, okay, there should be space below the workpiece. So I need to move it slightly ahead. So what I would do is, that is one point. And the second point is, okay, if you see these 2 support pins, are towards the center of the component or the workpiece. It is always better that I move them towards the end of the component so that they are supported well. Let me measure what is the distance. Using the measure tool, I'm going to measure the distance between end of the workpiece to this plane. So what you are seeing here is, okay, that is like 40 mm. 40 mm. Okay. So now I'm going to come back to the base plate. So now what I would do is I have this sketch for the positioning of the support pins. So what I can do is I'll just go to properties and then come to the feature properties. This is like sketch 2. I'm going to put the feature name as support pin positions. So what happens is it will be very easy for me to identify. So support pin positions, I know if I'm going to edit this, when I change this, the position of the support pin is going to get altered. So what I will do is I'm going to put this as 10 mm. And then I'm going to add an additional 30 mm to this because I have measured 40 mm there. So this will become 90. So now this is how it is looking. Let me come back to my drill jig assembly, update all. Now you can see that the support pin is not below the hole. And then the remaining 2 support pins are supporting the workpiece. Now this is something good. So now I have made the support pins on which my workpiece is located. Let me save the file. Always keep in mind, okay, we need to keep saving the file so that there is no data loss. Sometimes due to system resources, the CAD programs could crash. So whenever a CAD program crashes, okay, you might lose the design data. So I always recommend that keep saving frequently. So now let us move to the next step. The next step is to design the locators. Let us design the locators. File, new. Let me show you my design, how I have done it before we get into designing it. Let me hide the top plate. Let me also hide the clamp. If you see here, I have the front locator and then I have two side locators. And these locators are mounted on support pieces. These support blocks, okay, if you see, okay, it has got a very peculiar shape. Let me show it to you. You can see this is how the shape is. Okay, it is like something like an inverted L or something like a P. Let me come back, let me close this file and come back to my original design. Why have I designed like this? Okay, what am I trying to do? So basically what I have here is, okay, I have this is called a wear plate. What happens is when we are loading and unloading the workpiece, hundreds of them. So the tendency is that, okay, this will wear out because metal to metal, hundreds of times, okay, you are adding it, removing it, adding it, removing it, or in other words, loading it, unloading it, loading it, unloading it. So the tendency that this will wear. So what we want to do is we want this to be hardened. This is to be really hard than the workpiece so that it doesn't wear very easily. So I made it as a separate piece. And then this shape, okay, which is very peculiar, which comes from my experience of designing hundreds of jigs and fixtures, is this shape is always very easy to manipulate a jig or a fixture. What does it mean by manipulation? Because whenever, okay, we are manufacturing, okay, there is a tendency that there will be errors, human errors, either they are not machining it properly. Most of the times, okay, they would machine it properly, but there are chances that there could be some human errors. There could also be some machine errors. There could be some vibrations in the machine. So we might not get the accurate measurements while machining. So variety of things could happen. So what happens is we need to locate this workpiece precisely. That is, when I drill the hole, the drilled hole should be at 25 mm from the edges. So for that, the distance between these two wear plates, okay, is very, very important. How much distance I should maintain, that I'll have to derive mathematically. It's not, I can't derive it just without any mathematical calculation, okay, which we'll calculate it later. But let us assume, okay, I have made the design and then still because of the human error and the machine error and some unforeseen errors, the distance between these two plates is not what I wanted it, or is not something which I had designed, but in the actual manufacturing, okay, there is an error. Either the gap is more or the gap is less. If the gap is more, what I need to do? I need to push these locators towards the workpiece. If the gap is less, okay, I need to push them away. How can I do it easily? once all the components are manufactured. Let us assume the gap is less. I need to move them back. So what I can do is I can take this wear plate and then machine this surface. What I can do, I can take this wear plate and machine this surface. Or I can take the locator and machine this surface. So what happens is the gap will increase. Okay. Or let us assume the gap is more. I need to put the locators closer. I need to put these locators closer. Then what I can do is I can machine this surface of the locator. So when I machine, what happens is this will move forward. I hope okay, you have understood the concept of making the locators like an inverted L or a P shape. So that will help me in adjusting if at all if there is an error which is coming while manufacturing. Okay, that's the concept. However, what happens is here I don't have that provision of making an L shape. Here, okay, I was able to make it as an L shape because I'm mounting the locators on the side of the plate, not on top of the plate. Whereas here, okay, I've provided a U slot. This U slot is used to clamp the jig on the drilling machine. I hope all of you have seen the drilling machine. Anyhow, okay, just for the sake of clarity, let us just look at a radial drilling machine. Let us look at some images of radial drilling machine. So this is one of the radial drilling machine. You can see that there are T-slots on the radial drilling machine. So what we can do is we can mount our drill jig, the drill jig into the T-slots. So I have provided the U slots. So what happens is the drill jig will be firmly clamped to the radial drilling machine so that the operator can work more conveniently. But it is left to the discretion of the operator whether he wants to clamp it or he doesn't want to clamp it. Okay. It's not mandatory that the drill jig has to be clamped. But as a designer, I'm going to make a provision for clamping. So now we have the U slots here for clamping. So because of the U slot, I am unable to make this locator in either inverted L or P shape. So now how are we going to handle it? So here again, I have the wear plate here. So the wear plate is mounted onto this block. And what we need to do is if at all, if we need to adjust, either we will have to machine this face or this face. If we want to put it back, if we want to put it front, how are we going to do it? Then what we need to do is, okay, we need to put some shim behind this wear plate. What is a shim? A shim is nothing but a thin plate, a very thin plate, okay, which could be inserted inside so that the wear plate will come forward. So this is something, okay, which is very important. We need to anticipate, okay, how our design could go wrong and then make provision for adjustment at the later stage after manufacturing. So this is something which is very, very important. The designer should be able to anticipate the problems from the functionality point of view, from the manufacturability point of view, even from the design point of view. So this is the design what I recommend for the locators. So let us go ahead and make the wear plate first, the wear plate. File, new part, as usual, create a part with the name as wear_plate. Now I'm going to use the position sketch. Okay. And I'm going to put a rectangle, a centered rectangle. And put the dimensions for the length and width. The sketch is fully constrained. Maybe I'm going to put this at 25 mm and 30 mm. Or maybe 40 mm. I'm going to create a wear plate, maybe some 15 mm to start with We will adjust it later. Now I need to create a hole. So now I need to create a hole for fastening this wear plate onto the block. Let us go back to the original design what I have created. I need to fasten, let me hide the component. I need to fasten this wear plate onto this block. So either I can make a countersunk holes or a socket headed hole or a counter bored hole for socket headed cap screws. Let me come back to the wear plate. First, let me try the counter bored holes. I'm going to create a hole on this face. I'm going to make it a through hole up to last type. I want a counter bored hole, and standard. I'm going to use metric cap screw, probably M4. Okay, looks good. Let me go with M6, slightly higher, and I'm going to position. As usual, last time, okay, we created, this is the center of the hole. Let me create the dimension from the center. And I will create a dimension, another dimension, the vertical dimension. The vertical dimension, I will make it 0 time being. And then this, I will make it some 20 mm. Or not 20 mm, maybe some 15 mm. Let us see. It is coming outside. I'm going to change that to 10 mm. So now I have one counterboard hole for metric cap screw or socket headed cap screw. If you don't know what is a socket headed cap screw, let us have a look at it. You can see this is the socket headed cap screw. So using this socket headed cap screw, we are going to clamp the wear plate onto the locator. So now let us create the block. File new part. I'm going to call this as a wear plate block. Let me create a position sketch on the YZ plane. I'm going to create, this time I'm going to create a rectangle. And what I would do is I'm going to use the dimensioning scheme like this. I'm going to put one dimension from the horizontal axis to the bottom, one dimension from the horizontal axis to the top, and then one dimension for the length. I'm going to make this line and this line symmetric with reference to the vertical axis, symmetry constraint. Now, if you observe, I have this dimension, I have only one dimension given, whereas here I am giving two dimensions. Why? Because this is going to sit on the base plate. So the thickness of the base plate, what I have given is 20 mm. This I am yet to decide. I don't know how much this is going to be. We'll decide it. So tentatively, I'm going to put it at 30. Let me give one overall dimension reference, because once I have defined these two dimensions, this is going to be a redundant dimension. So this has to be a reference dimension. So now what I would do is I'm going to create a pad of 20 mm preview. Okay. Maybe I'll make this 30 mm. Now what I need to do is I need to make the cutout. So for that, what I will do is I will again create a position sketch. I will select the center plane. Okay. Now what I would do is I will create a rectangle here. I'm going to align this with the horizontal axis. Okay. Now I'm going to put this dimension. Maybe I'll put this at 10 mm. Let us see. We'll fine tune it later. These dimensions are something extra what I'm creating. This can be like 1 mm to 5 mm. Nothing to worry. Or it can also be 0 mm, but generally, okay, it is preferred that it should be slightly higher. And then now what I would do is I will create a cutout or a pocket on either side. Click on more and then up to last on one side. That is the first limit. The second limit again up to last. Preview. You can see a cutout has been made. Okay. Now I'm going to save the wear plate block. So now what we need to do is, okay, we need to create a subassembly. It's always better to create a subassembly because they will be clamped before assembling to the main product. In the sense, okay, let me explain you in detail. So now what I am doing is I am trying to create assembly of these two components. That is, I am trying to create a product because before assembling to the base plate, these two should be clamped. That's the whole idea. So I'm trying to kind of replicate the manufacturing process, okay, into my design itself. So that I'm telling them, okay, assemble these two first, okay, then assemble these two to the base plate. Because if you want to assemble these two individually to the base plate, it could be slightly difficult. You can observe, right? Okay, how would you tighten a screw? It would be very inconvenient for the assembly technician to assemble a screw here. But if they are assembled outside the jig, okay, it will be very easy. That's what I'm trying to tell. So let's create a new product, that is a sub-assembly. Okay. And let me name this as side locators. Side locators. Save the side locators. So now what I'm going to do is I'm going to assemble the wear plate block and then fix it because this is the first component. Okay, it's always better to fix this component. And then what we can do is again we can existing component with positioning, select the product and then bring the wear plate. Where is my wear plate? I don't have the wear plate here. So probably I haven't saved the wear plate yet to hard disk. Let me go to wear plate, save it to hard disk. And then I have only one hole. I need to create the other hole. So let me take this hole and then use the mirror command. Mirror with reference to this plane. Okay, so now I have two holes. Let me come back to the side locator product. Existing component with positioning, select the product. Now I can bring the wear plate. As you can see, the wear plate is inside the locator. Let me use the manipulator and then move this. Now I can give the contact constraint between the behind the wear plate and front of the block. And then I can align this plane and this plane. Okay, looks good. And then from the height point of view, let me give a distance constraint from this point to this point and just give some 5 mm. This is how it comes. Okay, looks good. Now let me come to the drill jig assembly. In the drill jig assembly, now I need to assemble the wear plate and the locator block. I'm going to use the same command, existing component with positioning. Come to the product. I'm going to take the side locator. Okay. I'm going to use the manipulator. In the Y direction, X direction, so it will move it behind. So now I need to assemble it here. If I'm going to assemble it here, I think it should be okay, not a problem. Let me assemble it. I'm going to put a contact constraint between this face to this face. Again, a contact constraint between this face to this face. Now it is sitting perfectly. So now I need to put a distance constraint. A distance constraint between this face to this face. Maybe I'm going to put it as minus 60. So now I have one of the side locators positioned on the drill jig assembly. So now I need to put the other side locator here. But as per the concept design, okay, we have a clamp also coming here. So what happens, let me show you the original design, what I have done. As you can see here, let me unhide the clamp. So I need to have some space for the clamp. So if I have to mount the side locator on this face, okay, that is going to be a very big component. So what I'm trying to do is I'm trying to put a cutout in this fashion on the base plate. So let me replicate that on the base plate. Let me come back to my base plate component. So now I think one point all of you might have observed. The design is happening simultaneously on all the parts. This is something, okay, which all the mechanical engineers should understand. The design can't be done on individual parts. So we will have to work simultaneously on all the parts. Then only, okay, we will be able to do a better design. And then only, okay, we'll be able to do justice for the design. Why I'm emphasizing on this point is, this is a simple design because this is mostly done for training purposes. We have taken a simple problem and then we are trying to solve a simple problem. Let us assume, okay, you have a complicated problem. What could be a complicated problem? A complicated problem could be you are working as a designer, a product designer, where you are responsible for designing some components, okay, within the car itself. So then you can't design it in isolation. You have to design along with your colleagues who are responsible for designing the surrounding parts. Sometimes the colleagues could be part of other company, other geography, which makes it very essential for mechanical engineers to have very good communication, because you can't do something in isolation. So that is one of the strength, or that is one of our USP at Royal Mechanical, where we have experience of working for large multinational companies, where probably, I don't know, okay, this is the first of its kind, okay, where somebody is doing a live design, explaining a live design, how it is done. Or else, okay, most of the YouTube channels or the training companies, okay, they teach only commands, CAD commands, and CAD commands anybody can learn, okay, who has access to a CAD software. But design is something only an experienced person who has experience of working for industry can only do. And then because it's a training program, we can only take up simple problem statements, or else the training program will become so lengthy, most of the learners, okay, would lose interest. Anyhow, okay, let me continue. So I'm going to put a cutout in the base plate. I'm going to make a position sketch here on the top surface of the base plate. I'm going to swap and then reverse V. Reverse V. I'm doing this again and again. I'm going to swap whenever I'm going to create. I'm going to swap and then do the reverse V because I always want a top view. Because there is a repeatability. You see, always I intend to keep this as the top view so that my visualization is always perfect. Perfect in the sense there is consistency in my visualization. I'm always looking at this as the top view. If you keep on changing the orientation, that might not be really consistent and then some errors could happen. Let us create the position dimensions for this rectangle. If you see again, I am taking a very unique approach for dimensioning. Let me explain you. See here what I have done is this dimension can be 0. This dimension also can be 0. Okay. But I always recommend that you keep this either 1 mm or 5 mm so that it always comes outside. Because sometimes CAD programs might give error. Not really, but it's a best practice. Okay, when we are doing CAD designs, that we don't align these to the edges. Okay, it comes outside, no harm. Okay, in coming outside, it is going to cut the plate. And what I'm doing is this, I'm going to keep it as a variable so that I can alter them. Maybe this I'm going to keep it as some 80 mm or probably 100 mm time being. I will adjust it later. Exit the sketch and then create the pocket up to last. Okay. So now we need to add a fillet here, edge fillet. I'm going to put that as some 5 mm. Okay. So now this edge fillet is very, very important. How are you going to machine this pocket? You are going to machine this pocket, okay, with the milling machine. Without the milling machine, okay, you won't be able to do it. And then the milling machine cutter is circular in shape. So I'm going to put a 5 mm radius so that we can do this with a 10 dia milling cutter. You can't keep this sharp. If you keep it sharp, it's not that, okay, we can't make that sharp edge, but it will become very costly to make that sharp edge. And then it is insignificant. Why do I need a sharp edge? It has got no functional requirement to be sharp. So it is always better to make it, to provide some radius, slightly higher value, so that it's easy for manufacturing. So now keep saving. Don't forget to save the design frequently. Come back to the drill jig CAD product. So now let us assemble the side locator. The same command, existing component with positioning. Select the side locator. Okay, I want to use the manipulator, slightly move it. Why I'm positioning it? So that it will be easy for me to assemble. Provide a contact constraint, this face to this face. Provide a contact constraint from this face to this face. Update. So now I have. So what I can do is now I can provide a coincident constraint between this face to this face, because ideally they lie in the same plane. I don't want them to be in a different plane. Now you can see. Now you can see what has happened. So now it is interfering. So what I can do is go to the base plate and then now you know what dimension to change. And now you can appreciate the way I have changed the dimensioning scheme, or the way I have done the dimensioning scheme. You see, I have kept this independent dimensioning so that I can alter it in this direction without much of difficulty. Let me put this as 50. Come back here to my drill jig, update all. Now it is looking good. But here we can see that it is interfering. So what does that mean? That means, okay, we won't be able to assemble this locator if we design like this. So it is better, okay, we have 10 mm gap. Let me measure this distance to this distance. It is 10 mm. So I need additional 10 mm. So what I would do is, I would go to the base plate and put an additional 20 mm here. Instead of 100, I can put it as 120 mm. Okay, now this is looking good. So now what we want is, okay, we would want the front locator. We can put the same wear plate probably. And one thing I forgot to tell you is we need some gap here. Because whenever we do the drilling, there could be some burrs, okay, which are going to fall on the drill jig. So if at all, if there is no gap here, okay, it might get stuck here. So we need to have provision so that the operator can clean the burrs from the jig very easily. What they use a brush to clear the burrs, or sometimes, okay, they also use some pneumatic air to blow away the burrs. But generally the brush is the most preferred because you have control on where the burr is flying. Because if you are using a pneumatic air, what happens is the burr flies and then it can fly and enter the machine. So what happens is the machine could get spoiled. So a lot of companies don't prefer to use the pneumatic air to fly the burrs. But a lot of companies also use it, but I generally recommend to use a brush, not a pneumatic air, to throw away the burr so that you have control on the burrs. We don't want burrs to go and fall where it is not intended. We also have to protect the machine because machines are quite costly. And then if we can't protect the machine, we might generate loss for the company. And then, mind you, okay, the mechanical engineers are responsible for saving money and then making profit for the companies. So now let us create the front locator. As usual, create a new part file. Front locator block. I'm going to create a position sketch on the ZX plane. I'm going to create a rectangle. If you observe the sketches, the way I'm creating is I'm always creating the sketches mostly the way it gets oriented in my drill jig. I'll explain it in detail later. Let me create the dimensions. One for the length, the other for the width. And I'm going to apply a symmetry constraint between the top edge and the bottom edge with reference to the horizontal axis. Apply symmetry constraint. Let me change this to some 50 mm. Not 50, let me change this to 80 mm. And this to 25 mm. I think I made a wrong sketch. If I'm going to put this into the top view, it is coming like this. Now, this is not the way I want it. Let me put it into the isometric view. I want this to be in the same fashion as it would look in the top view. So what I will do is I'll take the sketch object, change the sketch support. Now this sketch is on ZX plane. I'm going to put that into XY plane. Okay. But still, this is not the way it is supposed to be in the top view. Edit. If I put this into the top view in the sketch mode, you see, this is how it is coming. I don't want it like this. Let me exit the sketch, delete it. This is what I was trying to explain. I'm going to create the position sketch again on the top plane, that is XY plane, swap it reversely. Now I'm going to make the rectangle in this fashion. Add dimensions to the length and the thickness. I'm going to make this some 80 mm and this 25 mm. Apply symmetry constraint between the top line and the bottom line with reference to the horizontal axis. Symmetry, okay. Exit. Now, if I'm going to put this on the top view, now you see this is how it gets assembled on my jig assembly. Once I assemble, okay, you will have an idea. So let me create the pad, probably 50 mm height. Let us see. Tentatively, okay, we'll have it like that. Save the front locator block. File new. I'm going to create a product for the front locator block. So I'm going to assemble the front locator block. Where is my front locator block? Fix component. The first component, okay, it's better to fix it. And now what I would do is I'm going to save the product front locator. Save. Now I can assemble the wear plate. And we want to use the same wear plate. Because I'm using the wear plate in multiple locations, the orientation is changing. No, nothing to worry. Let me use a manipulator and slightly move it away. I'm going to create a contact constraint between the front face and the back face of the wear plate. Then I can align the center planes. Okay, and then I'm going to put some distance constraint, 5 mm above, -5. Okay, this is how it is. So now what I would do is I would put this front locator into the drill jig assembly. I'm going to come here and use the existing component with the positioning. Existing component with positioning. Use the front locator. Now you can see the front locator, the orientation of the front locator is perfect. Only the positioning is varying. That's the way, okay, we should design the 3D models. Use the manipulator in the Y direction. So now what I would do is I'm going to apply the contact constraint between the front of the wear plate and the front of the workpiece. And the contact constraint between the bottom of the front locator block and top of the base plate. And coincident constraint between the planes. So now it will perfectly assemble. So if you observe, all the components of the jig are getting assembled to the workpiece. This is how we will design. Nothing wrong in it. This is how it has to be done. So now what we can do is, everything is looking perfect. Now we can add the U slot. To add the U slot, okay, we need slightly more length. I'll just put it as 150. Maybe here also I might need slightly extra. 30. Looks good. Let us sketch the U slot. I'm going to take the position sketch, select the top surface of the base plate, swap, reverse V. Okay. So now this is the center of my workpiece. So I will put the U slot there. So what I would do is I will use this elongated hole command to create the U slots like this. Let me put dimensions for the radius dimensions. I prefer the radian dimension. Delete this. Again here, the radius dimension and delete this. Put the depth dimension. Maybe some 30 mm depth would be good for the clamping purposes. So now we can put this extra dimension. This is something which is going outside, so we don't have to worry. We can have this additional 30 mm or something like that. But still the sketch is not fully constrained, because the positioning has to be done. So I'm going to apply a constraint between the center of the elongated hole and the horizontal axis. Let us put that as coincident and then see. Okay. So it's about the length of the oblong hole. Okay, now it is fully constrained. Okay, that's not the problem. The problem is with the horizontal constraint. We need to provide horizontal constraint for these two lines as well. Some 15 mm or maybe 10 mm. How do we decide this? This should be the same as the size of the T slot on the drilling machine. So right now I'm assuming the size of the T slot is 20 and I'm going to provide a width of 20 mm. Now we can create a pocket up to last preview. Okay, now we can see the U slots are ready. Let me come back to the drill jig and then observe. We have the U slot, we have the locators. Everything is okay. Let me update all. Looking good. Had some problem. Because I increased the length in this direction, the locators also moved in this direction, which I don't want to. So what I would do is, I need to change the constraints so that it doesn't alter in future. So this product 7, okay, we need to identify the constraints of product 7. So what I can do is right click product 7 component constraints. You can see the component constraints are getting highlighted. The 60 mm I have given to this face. So if I alter this, this is also going to get altered. So what I will do is I'm going to select this offset constraint and I'm going to redefine this constraint definition. Click on more. So now this is the base plate And then this is the wear plate. Wear plate, let it be the same, nothing to worry. But the base plate, I need to reconnect. I'm going to reconnect this to the workpiece because the workpiece is not going to change. Workpiece is going to stay there. Remember, we have fixed the workpiece. That was the first component. Okay, we put into the assembly. And then this is coming as minus 60. Instead of minus 60, what I would do is I am going to put this as 10. Let us see. Now you can see. Instead of 10, maybe 20. Minus 20. Minus 20 is too much. Probably minus 10. Okay, now this looks good. This also looks good, but here we have an interference. We won't be able to assemble the locators on the base plate. Let us measure the distance between this and this. This is like 30 mm. So I need to add another 10 mm, 40 mm. I'm going to go to the base plate, update this, and then put another 40 mm, additional 40 mm, plus 40. Now come back to the drill jig. Now you can see things are good. Probably we can slightly increase the length in this direction. 160 mm. Okay, it is looking good. Now let us save. Let me use save all so that whatever I have modified, they all will get saved. So now I need to design the clamp. Let me design the clamp. A strap clamp. First thing what I would do is I will create the product itself first and then save it as a strap clamp. Before we proceed further, I will explain the strap clamp from my original design. Let me open the strap clamp. This is how the strap clamp is. So I have a strap. On the strap, I have an elongated hole. Inside the elongated hole, what I am doing is I am going to insert a stud. And then I have a nut and a washer and a nut and a washer on the top as well. Here what I have is I have a bolt and a nut. So if you come back to the original design, you can see here. Let me show the workpiece. You can see here. This bolt is assembled onto the base plate and then it is tightened using the nut. Okay. And here we have a stud, which is again assembled to the base plate and then it is positioned using this nut. So what we can do is, if we are going to tighten this nut, a pressure will get applied on the workpiece. Okay. It's easy. It's easy. If I'm going to tighten this nut, in return, this strap is going to apply force on the workpiece and then it is going to get tightened. If I loosen this, what happens is I have put a spring here. Because of the spring, the strap will slightly go up and then it will be easy for the technician to take away the workpiece. So he has to slide it. He has to slide it in this direction. Okay, that's how it is. Clear, right? If you have any questions, okay, feel free to post the questions in the comment section. I will answer them in a reasonable time frame, nothing to worry. So let us design this strap, and then this is generally positioned at the center. The stud is positioned at the center, and then we don't want this to go forward. Okay, we would always want this to go back only, and then apply the pressure at the center of the workpiece. So let us design it. It's a pretty simple design. I have too many windows open now. Let me close some of the windows. The designs are not yet complete. We will complete them once we finalize other parameters. Let me keep this original design open. I might need it. The support pane. This is my actual jig where the work is in progress, or I'm designing it right now. Let me save it. Rectangular plate, probably I'll close this, I don't need it. Strap lamp is something, okay, which I'm working right now. This, I don't need it. Okay, so now I have closed most of the unwanted windows. Let me get started with the strap clamp. Now I have the product ready. Product is nothing but the sub-assembly. Now I'll create the part. Let me create part strap. As usual, okay, I'm going to create it in the same orientation, the way I want it in my assembly. I generally prefer to go to the top view. And then this time around, I would create a rectangle, a center rectangle. At the center at the origin, let me create the dimensions, strap width, strap length. This I'm going to put it at some probably tentatively 30 mm, and then this I'll put it at some 100 mm. 100 mm is 10 centimeter. This is a very small jig what we are designing, but however the concepts apply for all sizes. Here what I would do is I will go for another additional 30 mm height. Let me make a cutout, position sketch. The orientation is perfect for me. Let me create a rectangle. So what I would do is I would create the cutout depth and then the cutout length. So now these are extra, which I had explained earlier. I would generally keep them 5 mm extra because I don't want to go inside. If at all, if the orientation changes, okay, while you are sketching, click this command, normal view. So this will bring back the sketch orientation normal to the screen. Five mm extra. Depth, probably I'll go with some 10 mm to start with. Later we'll see what to do. And then this 60 mm is, looks too much, probably 80 mm. And then I'm going to create a cut, that is a pocket on both sides up to last, and then second limit also up to last. So I have the strap. I would provide a chamfer from 45. This is also possible, or you could also provide a fillet like this. 10. This is also good. So we'll have a point contact. This is also acceptable. What is the difference between the chamfer and this fillet? You see, making this fillet is tough from a machining point of view. But whereas the chamfer is easy to make. However, we will have to machine, that is, both of them are material removal processes. They are going to take time. But making a curved shape would take more time than making a straight face. So chamfer from the manufacturing point of view, radius from the functional point of view. So you can go with either the chamfer or the radius. And next, what I would do is I'm going to create a oblong hole. Let me create a position sketch on top of the strap. Top view. I'm going to swap and then reverse V. Okay. And then what I would do is I would create a elongated hole. I would prefer to pivot in the sense the position of the stud to be at the center. So what I would do is I would apply a dimension from here to here and then make this 0. And then I would apply a dimension from here to here. That would be the dimension for the movement of the strap, if at all, if I want to put it backwards. So let me put 10 mm time being. I would prefer to put a radius dimension here and then delete this linear dimension. Or 5, probably I'm going to put this as 10. And then these two should have a constraint, vertical constraint. So now everything looks good. I'm going to exit the sketch and make the cutout using the pocket command up to last. I'm sure you are observing it has become very thin and weak, which is not acceptable. However, okay, we will proceed and then adjust the things later. So I'm going to save the strap, come back to my strap assembly, and then assemble the strap, existing component with positioning, assemble the strap. As it is the first component, I'm going to fix this component. Okay. So now I need to design the stud. Let me create new part as usual and then create the stud. Create a position sketch and then create a circle. Apply a diameter constraint or a diameter dimension to the stud. Let me go with the M12 stud. I'm going to create a pad. Timing, okay, I will go with some 100 mm length. Save the stud. I need to create thread both on top and bottom. So for that, what I would do is I'm going to select the thread command, and then lateral face, I'm going to select this face. Limit face, I'm going to select this face. So now this is going to create a thread. Ideally, whenever we are creating the thread, the engagement of the thread should be 1.5 times the major diameter. As I am selecting the M12, so that is the thread diameter. So the engagement should be at least 12 plus 6, that is 18 mm. So what I would do is, to be on the safer side, I am going to make the thread depth as 25 mm. In the sense, I am going to create 25 mm thread depth, whereas I would keep the engagement at least 18 mm. Engagement with the base plate. So the thread depth would be 25 mm. You can see 25 mm thread depth. Let me do the same thing on the other side as well. Later we can adjust the dimensions. Lateral face, and then limit face 25 mm preview. Okay. Let me put it into the wireframe. Okay. I think it will be visible in the drawing once we make the drawing. It is better, okay, we create a chamfer. We create a chamfer in both the edges. Timing, okay, I'll keep that as 1 mm, 1 into 45 degrees. Now I'm going to come to the strap product, strap clamp. And then I'm going to assemble this stud. The existing component, select the product, select the stud. I'm going to put an coincident constraint between the center of the stud to the center of the oblong hole, one of the edges. And then I'm going to put a offset constraint between the bottom and the bottom of the stud. I'm going to put that as some 60 mm. Let me see how it works. Time being, okay, let it be like that. So now the stud size is 12, whereas the elongated hole dia is too much. Anyhow, okay, this portion has become weak, so let us adjust it. So what we need to do is, okay, we need to come and then we need to check what should be the clearance hole for M12 screw. Clearance hole for M12. You can see, okay, we'll get many tables. So what should be the clearance hole for M12? You can refer to any of the tables. M12 clearance hole, close fit would be 12.4. Normal fit would be 12.8. 12.4 is not essential. We don't want so close fit. Let us go with normal fit, 12.8 mm. So let us go to the strap and then change the diameter to 12.8. 12.8 divided by 2 would be the radius, that is 6.4. Let me save. Let me come back to the strap clamp. Now you can see it is perfect. Now the strap also looks quite strong. Let us put it in the top view so that it will be very clear. You can see there is a clearance. Now what I would do is I am going to make a nut. I need the nuts, the washer, and then the bolt, as I had explained earlier. So if we come to the original design, you can see here, I have the nut and I also need the bolt as well. So first thing what we will do is, okay, we will design the nut and the washer. File new part, okay. Let me design the nut first. Nut underscore M12. Okay. So basically, okay, it's a hexagon nut. So what we will do is we'll come here. M12 nut dimensions. So if we come here, what is interesting for us is M12 nut. What we need is the edge distance. S is across flat. We can also go with across flat or the edge distance E. So here what we have M12 is, okay, we have the across flat S dimension as 19. Let us come back to our CAD program. Create a position sketch as usual. I want to swap reverse V. So now here, okay, we have the polygon command. Select the polygon command, pick the center, and then put it like this. Now just provide the dimension across flat. What was the across flat dimension? 19 mm, right? For M12, 19 mm. So let me put 19 mm. The sketch is fully constrained. So what is the thickness of the nut? The thickness of the nut is M. M12 is 10 mm. So let me create a pad of 10 mm. So now I have it. So now I need to create a hole of M12. So I'm going to create a hole on the top of the nut, and then thread definition, it has to be threaded. Support depth is the type, that is entire threaded portion. I'm going to go with metric thick pitch M12, as simple as it is, but it is not at the center. So I need to, it's also not plain, it has to be up to last. I'm going to define the position of the hole using the position sketch. So what I'm going to do is I'm going to apply a constraint to the center of the hole and the planes. Coincident. Now again one more coincident with the horizontal plane. So now the position of the hole is fully constrained. Exit the sketch and look at the preview. Now it has come at the center. So now we have the sharp edges. You can leave it as is, no problem, but just for the look sake, what we will do is, okay, we'll try to make it look like a net. So what I would do is I'm going to make the position sketch as usual, and then this time around what I would do is I'm going to select the YZ plane. So on the YZ plane I'm going to sketch. What I need to do is I need to sketch a triangle. I'm going to use the profile command. This triangle, I'm going to put one triangle like this, and one another triangle. So now, as usual, I'm going to put the dimension, and these are extra dimensions which I always prefer to be outside. And then angle could be, provide the angle, and then let me create one axis at the center. This I can apply constraint to the top of the nut, coincide constraint. I'm going to use the quick trim command to remove unwanted edges. So now what I want is, I want to create a dimension. radius diameter. What is this? This is nothing but the across flat dimension, that is 19 mm. Okay. This also I want it to be 19 mm. So now this 19 mm should lie on this point ideally. So I'm going to change this to 0. I'm going to change this also to 0. And this can be 45 degrees. We don't have to worry too much because all we are trying to do is, okay, make it look like a nut. Now this extra can be 5 mm, but they are intersecting, so I'll just give 1 mm. Now they are not intersecting. If they are intersecting, the pocket won't happen. So now what I would do is I'm going to create a groove. And then preview. Now you can see that it looks like a nut. Very good. So now what we can do is we can assemble this nut to the strap clamp. So what I would do is I'm going to use the assembly command, existing component, and then I'm going to bring the nut temporal. I'm going to use a manipulator command, move it in the Z direction. Maybe I'll also move it outside so that it will be easy for me to apply the constraints. I'm going to put the coincident constraint to the center of the stud and center of the nut. And then what I would do is I'm going to put a distance constraint between the bottom of the nut and the bottom of the stud. So now here I want an engagement of 1.5 times the diameter. So that is M12 I'm using. So 12 plus 6 is 18 mm. So what I would do is I would put a 20 mm engagement. That is nothing but the entire thickness of the base plate. And then this is 10 mm. So 20 mm plus 10 mm is 30 mm. So my thread depth should be more than 30 mm. You remember I had put 25 mm. So I need to change that to 35 mm now. Now the stud is updated, coming back to strap clamp. So I have it. Now I need to create the washer. Let us go M12 washer dimensions. M12 washer, the small diameter is 13.5 and the outer diameter is close to 14 and thickness is 4 mm. 13.5, 14 and 4. Okay, new part as usual. Now this time it is washer underscore for M12. Leave the other options as is. Now sketch on the top plane or the XY plane. Swap reverse V. Okay. I'm going to create 2 circles. Coincide with the origin. One more circle. Now create diameter dimensions for both. Come back and then just check for 12 it is 13.5, 13.5 D and BC is 44 mm. 13.5, 44. Okay. 13.5, 44. And then let me create the pad. The thickness of the washer is 4 mm. So the washer is ready, saved to the hard disk. Let me assemble the washer to the strap clamp. I would need one washer here. Let me use the existing component with positioning, select the product, select the washer, M12. Okay. So now what I need to do is I need to coincide the axis of the washer to axis of the stud, and then provide a content constraint between the bottom of the washer to the top of the strap. Not bad, but the washer looks a bit big. Maybe let us go back and then look for some other dimension. Maybe this table. For M12 it is 13 and 28. External diameter is 28. M12. Okay, variety of washers are present. M12 small d is 13 and DC is 37 and thickness is 3.3. So variety of washers are present, and you no need to worry because we need to assemble a washer, and then a small variation in the diameters of the washer is not going to harm our design. It is not. It is going to be the same. It is not going to change our design. So let us go ahead with the washer what we have designed right now. Let us put one another washer here and at the top. Let me assemble two more washers. Washer M12. Okay. Coincide the axis of the washer with the axis of the stud, and then contact constraint between bottom of the strap and top of the washer. So why I'm trying to put washer here is I intend to put one spring in between. Let me put one another washer, existing component with positioning. Again, I'm going to go with washer M12. Okay. Coincide axis of the stud with the axis of the washer, and then contact constraint between bottom of the washer to top of the nut. So I can put a spring here. So now let us design a bolt, file new part. Okay. Bolt underscore M12. So what I need to do is, okay, it will be the similar design what we did for nut. Let us come back here, M12 socket headed cap screw dimensions. Yeah, I think socket headed cap screw or X-headed cap screw. X-head cap screw. Or we can just put it as bolt. M12 bolt dimensions. Yeah, I think this is pretty good. So M12, we have the head K, and then we have S across flat. It is the same 19 and yeah, 19. Only the K is changing. The thickness is 7.5. I think what we could do is we'll come back to our Catia, close this bolt M12, take the nut, and then what we'll do is, okay, we'll use whatever we have constructed here to create the bolt. So what I'll do is I'll do file, save as, check this save as new document, and then just select We don't have it, so we can put it as bolt temple. Save as a new document. So this is going to create a new document here on the local hard disk. I'm going to open that bolt temple. Bolt, okay. I have the bolt. Oh. Bolt temple from the local hard disk. So I have this nut which I have saved. So what I need to do is I need to just delete this hole because this is a bolt. So I'm trying to convert the nut into bolt. So let me delete this hole, delete aggregated elements, fine. And then we need to delete one of the chamfers. Definition, okay. I need to change the sketch. So what I'll do is I'll delete this bottom sketch, keep the top sketch intact. So I have it here. And then what I would do is I'm going to create a position sketch at the bottom. Swap, reverse, okay. Now what I would do is I'm going to create the screw portion. That is nothing but M12. Exit the sketch and then create probably length. I'll keep some 100 mm timing. I'll adjust it later. Maybe too much. Let me keep it some 60 mm. Apply a chamfer of 1 mm. And then create a threaded portion. Limit. Thread 12. And then depth I want 35. Okay. Depth is 35. So now what I would do is I'm going to come back to my strap clamp. And then assemble the bolt here. Let me use the same command, existing component with positioning. Select the product and then bolt M12. Now you can see that I did the save as command, save as same name, but as a different document. So it is conflicting when it comes to assembly. In the assembly, it is telling that we have two files with the same part number, nut M12. Whereas the file name is bolt M12. So I'm going to rename the part to bolt M12. Bolt underscore M12. Okay, I'm going to use the manipulator and then drag the bolt outside. So now what I will do is I need to create a coincidence between this plane and this plane. Okay. And then I'm going to give a contact constraint between the top of the bolt to bottom of the strap. Fine. I'm going to use a manipulator. Move it out. Now I need to create an offset constraint between this and this. Maybe minus 30. Okay. So time being, we can keep it like this. So now what I need to do is, okay, I need to put one more nut here and one more nut here. Let me assemble the nut temple. Okay. I'm going to coincide the axis of the bolt to axis of the nut. And then coincide the bottom here and here. Looks like, okay, they are interfering. Let us adjust it, okay, once we take it to the jig assembly. Here also it is interfering, but this is not the final design. Let me bring one more nut. Nut and all. Coincide the axis of the stud to the axis of the nut. And then contact constraint between the bottom of the nut to top of the washer. So now the strap clamp is ready. Let us come to the jig assembly. Assemble the strap clamp to the jig. Strap clamp, cat product. Assemble it. I'm going to move it outside. So now what I would do is I need to provide a contact constraint between the bottom of the nut to the top of the base plate. So that's where it is sitting. That is the first constraint. The second constraint is positioning. I'm going to put an offset constraint. I will put it with reference to the workpiece because the workpiece is not going to change. Here, I'm going to put this as -10. Okay, good. Now what I want is I'm going to put one more offset constraint between this face to this face. So I want this as -20. Let me put it as -20 and then see how it will work out. Fine. So now what we are seeing here is the side locator and the strap, they are interfering. So what we can do is either we can reduce the size of the strap or we can slightly move the side locators towards the front. So here is the dimension which was positioning. I'm going to change this to 0 and then see what will happen. So now you can see that I have prevented or I have avoided the interference, but still okay, it is very close. So what I can do is I can open the side locator and then see how I can alter the design. So now I can make this width and this width same. So the wear plate width is the wear plate width is 40 mm. So what I can do is I can also change the width of the block also to 40 mm. Okay, this looks good. I have saved the file. Now you can see that the side locators are far away from the strap. Now everything is fine, but I want this clamp to act at the center of the workpiece. So let us try to measure and adjust it. All other things look pretty good. I'm going to measure the distance between this face to, okay, I have a line here. Let me measure it. So this is 40 mm. The X dimension is 40 mm. That I want it to be 25 mm. So I need to increase it by another 15 mm. So what I would do is I'm going to open this and then increase the length by another 30 mm. I will change this to 130 mm. So this will become 110 mm because I increased it by 30 mm. So this also has to increase by 30 mm. So this will be minus 40. I think, okay, let me just check, okay, if this is at the center. I'm going to measure the distance between this and this, 20 mm. So I can adjust the position. So this can be minus 35. So now this is at the center. Now the clamp is acting exactly at the center of the workpiece. Let me save all the files. I think I didn't save for quite some time. Let me go to the strap clamp. So now what I want is, I want this to move slightly farther. Maybe minus 50. Good. This is looking good. But I need to reduce the length of the bolt. So this is, the dimension is 10 mm. So reduce the length by 10 mm. That is the pad. 50 mm. Okay, everything is looking good. Now, as you can see, the bolt has come outside. So what I would do is, I'm going to increase the size of the plate. Now you can see the advantage of this type of dimensioning. 120, I increase it by additional 20 mm. And then this, I will reduce it by another 10 mm. So maybe 150 mm. Oh, this is looking really good. Update. But this has come farther. So let me measure what is the distance. 20 mm. So I need to increase this slot by 20 mm. So I'm going to come back to the base plate. And then this will be additional 20 mm plus 20. Update. Now this is sitting perfectly all right. Everything is looking fine, but for the washers are looking odd. They are looking quite big. Let us go back and check the washer size. M12 washer. Small d is 24 mm. Oh, DC is 24. Small d is 10.7. How is that possible? M12, 13, 37, 3.3. 13, 37, 3.3. Let us check. Thickness is 3.3. Okay, this looks decent. Anyway, as I told earlier, if there is a small variation in the size of the washer, that is not going to functionally affect this design. We don't have to worry. Everything is looking good, but it is not clamping. The clamp is not clamping the workpiece, right? So we need to bring the strap still down. It can't be at such a height, right? Let us measure what is the distance quickly. So the distance from the top of the workpiece to, so this is 10 mm. So we need to bring everything down by 10 mm. I think it's possible. Yes, possible. Why not? Or the other way, what we can do is, okay, we can increase the support pins by additional 10 mm. That is also okay. What we can do is, we can increase the height by 10 mm. That is 20 mm. Looks odd, right? This is looking really very odd. This pin. So what I'll do is, I'll make this 15 and I'll make this 15. Now it is looking slightly decent. So now what I need to do is, the plate is assembled at a distance of 10 mm. You can see the dimension here. So that we can change this to 15 mm. Now this is good. Perfectly good. And still we have 5 mm gap. What we can do is, we can open the strap and then probably, okay, we can increase the depth by 15 mm. Okay, this looks good. And then we can add a small radius here to increase the strength. Probably 5 mm. What will happen? Yes. Now you can see that the clamp is holding the workpiece. So now what we need to do is, okay, we need to apply a spring here. Let us measure what is the gap. The gap is 23.4 mm. Okay, more or less, okay, we have done everything. Is there anything left? I have put the clamp. So the location is done. The clamping is done, but for the spring, we have the base plate. Oh, we don't have the top plate and the jig push, okay, which is very, very important. How can we forget that? So let us make the jig plate and the jig push. before we proceed any further. So let me make the jig plate. Position sketch on the top plane. Swap the horizontal and vertical axis and then reverse V. Now I'm going to create a rectangle. Create a dimensions for the length and the width. Apply a symmetry constraint between the top and the bottom lines with reference to the horizontal axis. Symmetry constraint. Let's make this 80 and this would be some 50 timing or maybe 60. Create a pad of maybe 25 mm height. Timing later we'll adjust it. Okay, the jig plate is ready. Now we need to create one product because the jig plate houses the jig push. So let me create a product, that is file new. Product which is nothing but the assembly. Let me save this assembly as jig plate. Both the part and the assembly file names can be same as the extensions are different. I'm going to assemble the jig plate. As it is the first component, I'm going to fix it. Okay. And then what I would do is I will come to my jig assembly and then assemble the jig plate. Jig plate product. Don't assemble the jig plate part, assemble the jig plate product. Okay. I'm going to apply a contact constraint between the bottom of the jig plate and top of this block. And then align the planes of the jig plate and the block or the wear plate, no problem. And then align the back surfaces of jig plate and the block. So now this is sitting here perfectly. I'm going to orient this to the top view. And then as you can see, we need to increase the jig plate dimension. Probably I'm going to make this as 90 timing. And then I'm going to create a hole on top of the jig plate up to last. I don't know what should be the dia. I'll just make it as 20 timing, position the sketch. I'm going to orient it to the top view so that it is easy for me to understand. Align the center of the hole to the center of the jig plate, coincide, and then apply a dimension. So let me apply this dimension. I'm going to put this as 30. Okay. Let me come to the jig plate and then see. The hole on the workpiece and the hole on the jig plate should coincide. So the hole has to move back. Let me measure the distance between the center of the hole on the jig plate and center of the hole on the workpiece. Is just 5 mm. So I need to move this back by 5 mm. Let me come to the jig plate and open the jig plate. Move this to 25 mm. Looks decent. So now we need to create the jig push, which will guide the drill so that the hole can be made. So we need the jig push dimensions. Let's go to Google and jig push standards for 10 dia hole. This is in inches. I think there should be an Indian standard for jig bushes. So let us check the Indian standard for jig bushes. Indian standard for jig bush. Okay, we have IS 666-1 published in the year 1972 for jig bushes. We can just check this file, and this is an authentic document, nothing to worry. So we need a headed jig bush of dia 10, that is D1 dia. So D1 dia 10 to 12. We have short jig bush and a long jig bush. Nothing to worry, we can go for the short jig bush. 10 to 12, the length L1 would be 12, and then L2 would be 4, L1 would be 10, 4, and D2 would be 15 or 18. 15 or 18. Okay, let's replicate this. I think these are the significant dimensions: D1, D2, L1, L2, and D3. Okay, we don't have to worry about the groove really, because jig bushes are not made, they are bought. Jig bushes are commercially available. So when I buy a jig bush, okay, it will come with the relief groove. So let us create the jig bush. File, new part, okay, jig bush. I'm going to sketch on the YZ plane. So what I would do is I'm going to make the profile of the jig bush. So I'm going to use the quick trim to remove unwanted portions. I'm going to make an axis at the center. Now I'm going to create the dimensions. Diameter, again a diameter. Height, the head. This is 10 mm. That is the size of the hole what we need to drill. So 10 mm. 12 is L1. Long is 20. So we will go with 20. And then L2 is 4. So this will become 16. And then the head will become 4. And then we have D2, which is 15. D2 is 15. And D3. D3 is 19. That's it. Exit the sketcher and then revolve using the shaft command, 360 degree. We have the jig bush ready. We haven't provided any chamfers or the radius because this is a commercial item which we are going to buy it. Once we buy it, we are going to get all the chamfers and the reliefs within the bush. So what we will do is we'll come to our jig plate product, and then here what I would do is I am going to assemble the jig bush on the cat product, not on the jig plate cat product. If the product is not active, double click and make it active. Assemble existing component with positioning the jig bush. Okay, so now coincide the axis of the bush with axis of the hole, and then provide a contact constraint between top of the jig plate and the bottom head. Update. Now you can see the jig bush is positioned, but however the dia of the hole what we made is very big. what I need to make is 15 mm. So this I want as diameter 15 mm. This plate can probably be, the size could be reduced. And this dimension could also be changed to 15 mm. Looks good, no problem. Now you can see that the drill jig is designed. So now what are the pending items in completing the drill jig detailed design, that is the 3D design. So we need to apply the spring, and then okay, it is also very important that we can apply some feet for this drill jig. It will be good. Maybe we'll have to adjust the length of the screws, and then we'll have to make all the holes for fastening these plates. Right now, okay, they're all sitting one, like for example, this block is sitting on this plate. This is possible only in the CAD. In reality, okay, if I place it, okay, this is going to fall down. So I have to make some holes and apply some fasteners to complete the design. The same applies with this block, this plate. Okay, I can't just place them. They are sitting because I have designed it in CAD system. In reality, if I'm going to put this block and then put the wear plate like this, okay, they're all going to fall down. So I will have to apply some fasteners. Okay, in the design, even in the 3D design, I'll have to apply the fasteners. I think for today, I'm going to close this live session. Probably in another couple of days, I will continue this design and take it to a closure, the detailed design. And then we have another major chunk of the design activity remaining. Let us go back and look at our design steps. You see, now we have designed the locators, we have designed the clamp, and then jig plate, base plate, everything is ready. So what we have done is we made the concept design, that is a sketch, and then we have developed the concept design into detailed design. But the detailed design is not yet complete. So once we complete the detailed design, okay, we need to put a lot of effort to create the 2D manufacturing drawings. Only once we finish this, the entire design data is ready for manufacturing. That is to seek approval for manufacturing. So what I would do is, I think another 1 hour for completing the 3D design, and probably another 3 to 4 hours to complete the 2D manufacturing drawings. Design is quite an activity. So now we need to use a lot of practical aspects while we are designing, and then we need to keep saving our data. It's not just about designing, we need to be able to retrieve our data for later modifications, corrections, upgradations, everything. So for today, let me close this session. And if you want me to create many such designs, could be on tooling like jigs, fixtures, press tools, which is my specialization area, and also product design, where I also have worked extensively. Do like this video. Don't forget to comment. Okay, if you have any questions, feel free to comment, and then share this video with as many mechanical engineers as possible. The more you like, share, comment, that will motivate me to create many such designs. And then our vision at Royal Mechanical is to provide you with job-oriented skills, industry-oriented skills, where you can create similar projects and then put them on your resume so that your job search could become easier. So for today, thank you all for watching, and bye bye, take care, all the best.